Over the last 25 years, I've had the privilege to work with a motley crew of image processing experts in Europe and the US, like Madi Samani on the screen here, working on data from Hubble and ESO, NOAA Lab, and lately also Webb. The universe has captivated human imagination for millennia. Is there a trick? It's not just me. Not just me. I'll keep talking while we call for help, right? The universe has captivated human imagination for millennia. Advancements in astronomical technology, particularly in imaging from telescopes on the ground and in space, have had a transformative power in altering our view of the universe and also fostering a profound sense of connection to the cosmos. When we stargaze, now it works. When we stargaze with lay people outside today, the most frequent question is there life out there? It's more frequent than questions about black holes or Mars or lunar landings that were number one some 30 or 40 years ago when I started that. And I think this is the result of our worldview slowly changing. The answer to the question about life is, of course, tricky. On the one hand, we know there are billions of worlds, likely life. On the other hand, it took a long string of seemingly improbable events. Among them, a mature galaxy, billions of years into its lifespan, forming a mature solar system with sufficient metals to form a rocky planet where water and life appeared. And then the moon creating the tides. Just the right conditions for life to emerge from those oceans. And then the little thing with the meteorite, 65 million years ago, changing the animal life on the planet dramatically from being dominated by reptiles to mammals. But still, we're gathered here in the Vatican with Webb and the other telescopes preparing the canvas for the most exciting time of scientific progress. Very, very fitting, I would say. The journey from monochrome to vibrant, high-resolution color images has been a pivotal element in broadening our cosmic perspective and redefining our place in the grand tapestry of cosmos. To highlight what I find to be some of the most pivotal visuals through history, we have here 1543, Copernicus showing the sun at the center of the solar system. In 1572, Tycho Brahe's bright supernova showing the heavens are changeable, nudging a revolution in astronomy. Of course, Galileo, 1613, the sunspots showing the sun is not perfect, but flawed. And 1785, William Herschel carefully counted the stars in different regions of the night sky, and his sister Caroline then produced this first drawing of the shape of our star island, the Milky Way. In 1859, Richard Carrington sketched this intense bright flare on the sun, A, B, C, D. This led to the Carrington event you might have heard of, the most intense geomagnetic storm in recorded history that led to fires in telegraph stations and would have led to electrical blackouts and widespread damage to satellites if it had happened today. Then in the 1890s, pioneering astrophotographer E.E. Bernard made these incredible photographs of dark nebulae, clouds of gas obscuring the more distant stars. 1919, Dyson and Eddington at the Eclipse expeditions, they verified this minute 2 arcsecond bending of light by the gravity of the sun, a visual proof of the mind-bending theory of general relativity. And of course, 1968, Apollo 8. William Andrews shot this Earthrise, and by some accounts, the most influential environmental photograph ever taken. It moved our vantage point and worldview even more from the Earth to space. And this image, of course, even more, 1990 Voyager 1 pale blue dot. We have seen that several times. We were now further out in the solar system. In the 90s, David Malin took these pictures of the heavens. They call him the man who colored the stars. And he showed these colorful views that definitely had an impact as well. And I think we should also take this one into the collection. 2015, NASA New Horizons, capturing an amazing color, high-resolution view of dwarf planet Pluto, exploding our perception of the diversity of worlds in the outer parts of the solar system. Of course, the observations and the scientific papers, they speak for themselves in many ways, but there is a lot going on under the hood, as Klaus also mentioned in his presentation, to visualize the data and to remove all the instrumental artifacts. And in many ways, it's maybe a new era in data visualization now with Webb and also the coming data deluge from Rubin. There are some design choices involved, and because of that, we have developed rigorous scientific standards. I hope Claudia will elaborate on some of them and we can have a nice discussion, but we do try to generate ethically correct images for the public. It's almost possible to generate a recipe with 6 components that go into these images. The first one is resolution, but not just angular resolution. I think Klaus also mentioned in his presentation, photogenic resolution, we call it. We defined that in 2013. So it's the field of view divided by the angular resolution. So large ground-based imagers can also make amazing images as long as you have a sufficient number of resolution elements. This image, by the way, was one of the first big Hubble mosaics, 15 pointings made in 2005 by our team of the Crab Nebula. To get definition and contrast, you need to compress the dynamic range in these astronomical FITS files that are so rich. And this is in many ways the secret sauce. After the astronomical processing, you then have to use a fetch function to bring those nuances into view so you can see them on a screen or in a newspaper. That work is done in our own interactive tool called the FITS Liberator. The inverse hyperbolic sine function is very diverse and flexible to handle most of the cases that we see. The colors are usually assigned as close to the astronomical filters as possible. But for Webb, as Klaus also mentioned, we use chromatic ordering, where the least infrared filter is assigned blue and the most infrared red. And then, of course, compositions. Entire books can be written about that. But the classical example is this one, Jeff Hester's Eagle Nebula from 1995, where the pointing of Hubble was so carefully prepared to work with Big 2's bat shape. Shows my age that I go back to these images here. Signal to noise has taught us many things, and we can achieve it with good weather or exposure time or large pixels, but also through modern noise reduction and sharpening tools. We now know that lay people, they need pristine depictions of space, so we need to remove all artifacts. It takes a significant amount of manual labor, sometimes hundreds of hours for gigapixel images. And just a case in point, we all know the diffraction spikes artifact from the secondary mirror mount, and it's almost impossible to remove, and as a result, has now permeated somewhat incorrectly into pop culture as these 4 spiked stars, or even 6 now with Webb. The actual pipeline we use is far more complex. No need to go into the details, but the post-processing and use of artificial intelligence tools really have led to a big step for us, an ability to cope with gigapixel images in this new era. So in conclusion, we have evolved from an understanding that we are the center of the universe, to the sun being the center of the universe, to having no center of the universe, and now maybe potentially on the cusp of discovering other worlds with life. When we do, if we do, our worldview will then change profoundly again. All eyes will then be on that world, and for a time that world may become the center of our universe. There's no doubt these are exciting times. Images are arguably the best way to share the momentous discoveries with the public. The huge data sets translated into color images do not only provide astronomers with information that lets us grasp these intricacies of cosmic phenomena, despite spectra, of course, delivering the real stuff. But images can kindle our curiosity and sense of awe and inspire this deep appreciation for the vastness and complexity of the universe, as long as we uphold strict scientific standards. And I'll let this run. It's a little slideshow that shows how a Webb image was made from scratch. Thank you for your attention.
All right, so we'll have time for one question. Colette?
I have a question about the diffraction spikes. So you said something about how they're kind of giving us a false impression of the universe, but I have found with my students that it actually resonates with them a little bit because, when we look at the night sky, we see diffraction spikes as well. I'm just curious if you've encountered that at all.
I mean, I think we see twinkling of the stars, but maybe less those pointy spikes that we see with the diffraction spikes. But I think it's interesting that it is now part of pop culture. If you ask any child to draw a star, and that's what they will draw because that's what they saw in the images. Hence, images is really what's leading their mind. Somewhat incorrectly, but okay, it doesn't matter so much. My point was more the fact that if we leave artifacts in the images, and we've done on a few occasions, it really comes back to bite us. We had images in a giant image that were like literally hundreds of thousands of stars that were saturated. And people wrote many letters about finding exoplanets. I'm not kidding. It's
One point that I can add about the diffraction spikes, it always helps to explain what they are, but I like to add them as it's the signature of the telescope. It leaves a little signature, and so you can see this one is Hubble, this one is JWST, and it's a cool party tricks to impress your nerdy friends.